I'm Randy McCauley. I'm with the Locus wash station. My other members are Roger Pierce, Stephen Snyder, and Ross. I'll go over some of the background, steady state operating curve, step response, first order plus dead time model, sine response, relay feedback, through Locus, and some conclusions. This is a schematic of our system with a pump, manual valves that we don't adjust in any of our experiments, a filter washing station, a transmitter. Can't think of what that is. Recording controller. And frequency drive. Block diagram of our system with our input variable, system, and the output. This is our steady state operating curve. It's fairly linear, but the slope does decrease throughout the regions as we go up in input percentages. This is an example of one of our step response experiments from 55 to 45%. The blue line is our input, and the red is our output. See, it doesn't follow exactly along it. It lags behind just a bit. These are Ks for our step up and step down experiments. They're fairly consistent within each region. This is our T naught for the step up and step down. They're also consistent with each region, and actually pretty consistent across the board throughout the operating range. Our tau for step up, step down. The last two, the higher two ranges, they're pretty consistent, but get more variation in the low to mid range between that step up and step down. This is our transfer function equation, output function, transfer function, input function. In the S domain, our input is 1 over S. Transfer function is what controls our system, and the output is C. Transfer function, K, our gain, T0, dead time, tau, or time constant. These are our first order plus dead time equations. Our input function, output, A is step size, A is gain, T naught is dead time, TD is time of step, tau is time constant. This is a model overlaid for one of our experiments. The green line is the model, and it pretty well overlays consistently with that. And we have a lot of variation within the actual data, but a lot basically along the center line. These Ks also include the model and SSOC, and again within each range they're fairly consistent, with the exception of the SSOC slope, which is a little bit higher than the low range. So our T naught with the additional data, and that the Bodian relay is the outlier in the lower three ranges of these. Another graph of our tau. Only the last one is really consistent. There's a bit of variation between the other three, the lower three ranges. One of our sinusoidal response experiments. The blue line being our input variable, and the red is our output. Response lagging slightly behind. Some of the measurements we took to get our system variables with a graphical method. Delta M is our amplitude of our input function. Delta C, the amplitude of our output function. T, time between peaks. And lowercase d is the time between peak of the output and peak of the input. We use that data to calculate the phase shift angle and the amplitude ratio and some of the uncertainties for each. We use these equations to find tau and T naught. of our Bode plots for a range of 25 to 100%. The amplitude ratio is on a log-log plot, and the phase angle is on a similar log. We lined these two up and found K graphically, as well as 1 over KCU, the controller gain. How we did that was we made a line at 180 degrees, came straight up, and the intersection point on the amplitude ratio plots, we found that. This is a similar graph, but the range is 75 to 100% here. The first region, 25 to 100%, the second was 75 to 100. The data is pretty similar between the two of them, with the exception of the time constant, tau. There's quite a bit of difference there. Now I'm going to go over the relay feedback experiment, the feedback control loop, and infinite gain, and operator between the floor and ceiling. Just an example of one of the experiments. The blue is the input function, the red is the output. Basically what's happening is every time the output crosses this line, the state of the input changes. Some of the graphical measurements that were taken to get our system variables: E, A over 2, delta C, the amplitude, and T, time between each phase. The average delta C over delta M was 2.7, the T 2.2, and B 4.3. Uncertainties are also listed. We use these equations to find KCU, omega FC, and 1 over KCUs. We just added that data to this graph, and K's are consistent within each region except for the lowest. And Bode is about half of what the others are. Same on the T naught. The previous data is similar, but the Bode and the relay, or this is amplitude, and the relay are different from the rest. Tau on the lower three regions is similar between all the experiments, and with the exception of the highest one on both is quite a bit lower there. Example of one of our group Locus plots. I see I've cut off some of the data, but it's going to be listed on the slide later. This operating range is 25 to 100%. This operating range is 75 to 100. KCU, K 1/4, 1/10, 1/500, and critically damped there. Some common damping ratios the customer may want. The 25 to 100 range, so critically damped KC 0.4, 1 over 500, 4.7, 1/10, 13.3, 1/4, 18, and ultimate damping 27. The values from the 75 to 100% range were basically the same: 0.4, 4.7 for 1 over 500, 13 for 10, 18 for 27 for ultimate damping. Conclusions: FOPDT models for the system step response were very close to the experimental results: K 0.1, T naught 0.7, and tau 0.6. In most cases, the coefficients found graphically were similar to those in the model and the Bode plots. Values of KCU were similar in the Bode charts, relay, and Locus model.
Somebody maybe has a personal while you're ready.
What's up is born ready. Good conflict.
You have to leave early, Jake?
Yes, fine. Should I leave now? She told me to be there 15 minutes early.
Let's stress.
All right, let's,
At least. Probably 30.
No.
Probably 30.
You said 30 on the
I think she said
You're
30.
gonna draw
I wasn't
something on
listening.
the board? No, no, it wasn't there.
we have multimedia on this one.
Yeah.